Hey Chem 20s, Mr. Riley here. Gonna do just a quick little video here on basic stoichiometry to help you guys along if you're struggling. In stoichiometry, what we're doing is we are using the chemical equation, the recipe, and the ratios from the balanced chemical equation in order to calculate how much of each ingredient or reactant that we need, or how much product that we're going to produce. And we can go from really simple to really complex stoichiometry. The first step that you need for any stoichiometry is you need to have a handle on producing balanced chemical equations. Have to. If you don't have this, you can't do stoichiometry well. And so we need to be pros at making balanced chemical equations. So knowing your composition or formation reactions, decomposition, single and double replacement, combustion reactions, and acid-base neutralization, which is usually like a double replacement reaction. And then also using your solubility table, determining if there's a precipitate, because sometimes maybe you'll just be asked about the precipitate and you have to determine what that is. And so you really need to have a handle. You need to be a pro at writing balanced chemical equations. And once you have a balanced chemical equation, you use the ratios from the coefficients from the balancing in order to do your stoichiometry. So let's look at a couple examples here. So these are, for those of you guys following along, examples from your Chem 20 Unit D workbook. If you know, what I would do is while I'm recording the video here, maybe pause it throughout and try to do these on your own. So whether you have a workbook or you can just do it on a piece of paper, you need a periodic table and your data booklet in order to do this. So first one is number 4 here, and this is a real simple mole-to-mole basic stoichiometry question. So the question says, how many moles of oxygen gas are required to react with 0.25 moles of iron metal? So in order to solve this, we need a balanced chemical equation. And so let's do that. Let's take some oxygen gas, let's react it with some iron metal, and we are going to produce here an ionic compound, right? We have a non-metal and a metal. So we got to look at the ionic charges to determine that. Oxygen is a 2 negative. Iron is a multivalent element, so it has 2 charges. So we use the one that is listed first on our periodic table, and that's the 3 positive version of iron. So when I put these together, I'm going to get Fe2O3. And I should have done my cation first there, but you guys kind of get the picture of that. And we're going to assume that that's a solid. And there we have it. Now we got a balance. And so when I'm balancing my equation, I'm going to look for sort of the biggest subscript and work backwards from that. So I see I have 3 oxygens over here, and then I have O2. You guys got to know your diatomics. Oxygen is O2. You're super 7 on your periodic table. And you just got to have it. Okay, so oxygen is O2. So when I see that 2 and I see this 3 over here, I know I need to get to a common multiple, which is 6. So I'm going to put a 2 here. I'm going to put a 3 over here. That gets me to 6 oxygens on either side. And now I can balance out my irons. I have 2 groups of 2 iron atoms here. So that's going to make a 4. So now I'm balanced. Okay. So now I'm going to look to my given information. So I have 0.25 moles of this, and I want to know how many moles of oxygen it's going to require. So that's my required information. So I'm going to start with my 0.25 moles of iron. Now to jump from one substance to another, you have to use your coefficients and your molar ratio between the 2 species. And that's stoichiometry. And so what I'm going to do here is I'm going to put what I want on top. This is called unit analysis that we're doing, or dimensional analysis. And so what I'm going to do is I'm going to take what I want on top. So I want to know the moles of oxygen, and I know the number of moles of iron that I'm using. And so I'm gonna get my ratio here from my balanced equation. So I need 3 moles of oxygen for every 4 moles of iron. And so moles of iron are going to cancel out in this equation. And if I plug this into my calculator, come on, turn on. I'm going to take 0.25 and I'm going to multiply that by 3/4. And I'm going to get 0.1875, and if I'm rounding that to 2 sig digs, I'm going to get 0.19 moles of oxygen. Okay? Stoichiometry right there. That's mole to mole stoic. Now we can add a second step or a third step to our stoichiometry, and this is where things get a little bit more difficult. So let's look at this question number 16. This one says, how many grams of aluminum bromide would be required in order to react with 0.1 moles of mercury metal? So again, let's start with our balanced chemical equation. So I'm reacting aluminum bromide with mercury metal. So aluminum bromide, I have to build this compound. Aluminum is a 3+ ion. Bromide is a 1- ion. So this compound is going to look like this, AlBr3. Let's move this up here. Okay, and we're going to assume solid because it's an ionic compound. We're going to react that with mercury metal. Okay. Mercury metal is a liquid, and we get that information from our periodic table. You guys should know mercury is a liquid metal at room temperature. So decide what type of reaction I have here. I have a compound plus an element. It's a single replacement reaction. And so I'm going to swap my metal with my cation. So first thing I'm going to have here is I'm going to have to go look and see mercury. What is the ionic charge of mercury? And mercury is one of those multivalent elements. And the first one listed is Hg2 positive. So 2 positive ion is the more common ion. So that's the one we're going to assume. And then bromine is a 1 negative. So when I put these together, I'm going to get HgBr2. I need 2 bromides for every 1 mercury ion. Okay, we can assume solid for that as well because it's ionic. And then we're going to be left with the remaining species, but it's going to exist in elemental form. It's not an ion, it's aluminum metal. So we're just going to have Al solid. Okay, now of course we need to balance this. And so I'm going to look to, again, we have this 3 and 2. If I'm looking at my bromide ions here, I have 3 and 2 here. So I got to get to 6. So I'm going to do a 2 here, and I'm going to do a 3 here. So now my bromides are balanced. Let's take care of our aluminum. 2 on the reactant side. So I put a 2 on the product side, and then we can take care of our mercury. 3 on the products. I need 3 on the reactants. Okay, and that will balance us out. Step 1, done. Now I'm going to write down my given information and figure out what's required of me. So how many grams of aluminum bromide would be required? Okay, well, how many grams? So that's a mass. So I'm going to be finding the mass of aluminum bromide to react with 0.100 moles of mercury metal. All right, so anytime, now this is going to be a 2-step problem here. Anytime we're dealing with mass, my students know you are going to need a molar mass for aluminum bromide. Okay, so we'll get to that in a second. So let's start with my given. This is my given. This is my required. So my given is my mercury. So I'm going to start with my 0.100 moles of Hg. I need to figure out from that how many moles of aluminum bromide am I going to require. So my moles of AlBr3 are what I'm looking for, and I have my moles of Hg, what I want over what I have, plug in my coefficients from my balanced equation, and it's 2 moles of this for every 3 moles of this. And then my next step here is now I have moles of aluminum bromide. I want to get to grams of aluminum bromide, and I have moles of aluminum bromide. So I need the molar mass. So my conversion factor here is going to be the molar mass, which I've already calculated to be 266.68 grams for every 1 mole of aluminum bromide. So I plug this into my calculator. I'm going to do 0.100 times 2/3 times 266.68, and I'm going to get 17.77, which for 3 sig digs, I'm going to round to 17.8. What's my units again? Oh yeah, grams of aluminum bromide are going to be required to complete this reaction. There you have it. Good luck, and I'll see you next time.